So the next thing we're going to do is we're going to calculate the surface area of a sphere. So let's kind of buckle up for this one. If we can parameterize a sphere of radius r using spherical coordinates, that's very, very useful to do it this way. Here, we're going to write that our sphere is given by having a constant radius, the number rho from our spherical coordinates is constant, and so our two independent variables are the theta and phi coordinates. So I just write in the sphere of radius capital R is given by capital R cos u sine v, capital R sine u sine v, and capital R cos v. So here I'm saying that theta, my first independent variable, is u, and phi, my second independent variable, is v. That gives me a parameterization, and my parameterization should go over the region where theta goes between 0 and 2 pi, and phi goes between 0 and pi, because those are the ranges for spherical coordinates. Then I'm supposed to take this parameterization, which I've rewritten at the top. First thing I do is I calculate these two tangent vectors. I take my formula for phi, and I just take the derivative with respect to u and the derivative with respect to v. The derivative with respect to u is the tangent vector tu. And so here it turns r cos u sine v into minus r sine u sine v. It turns r sine u sine v into r cos u sine v. And it turns r cos v, that doesn't depend on u at all, and so that turns into 0. That gives me the first row by taking the u partial derivatives. The tangent vector with respect to v is given by taking the v derivatives. R cos u sine v turns into r cos u cos v. R sine u sine v turns into r sine u cos v, and r cos v turns into minus r sine v. So that's the first thing we had to do. We had to figure out these two tangent vectors. Next, we're supposed to take their cross product. So we take those and we plug them back into the formula for the cross product using ijk, first vector, second vector. And we calculate it out. We get I times this little 2 by 2 determinant, which is minus r squared cos u sine squared v. We get j times the negative sign times this little 2 by 2 determinant. That gives us minus r squared sine u sine squared v, and k times this little 2 by 2, which turns out to be r squared sine v cos v, because we're going to get a cos squared and sine squared that get rid of each other. And then we take that, we rewrite it at the top again, and we're supposed to take the length, which is the square root of the sum of the squares of all of those things. So this squared is r to the fourth cos squared u sine to the fourth v. This one squared is r to the fourth sine squared u sine to the fourth v. And this one squared is r to the fourth sine squared v cos squared v. And there's a little bit of cancellation. We can collect together this cos squared u and sine squared u. And that turns it into an r to the fourth sine to the fourth of v. This one just kind of stays alone, and we can collect some terms together so that this becomes r to the fourth sine squared v plus cos squared v, and that middle term turns into 1, and so we're getting the square root of r to the fourth sine squared v. And so normally that should be equal to r squared times the absolute value of sine v, but in the range we're doing with spherical coordinates, that's just the same as sine v, because v was between 0 and pi. So the surface area is what we get by integrating this up. We integrate r squared sine v du dv from u is 0 to 2 pi because it's our theta coordinate, and v is 0 to pi because it's our phi coordinate. The first integral kind of plucks out a factor of 2 pi if you do the integral with respect to u, and the integral with respect to v turns sine v. If I integrate that from 0 to pi, I just get 2. And so we recover 4 pi r squared, which maybe we already knew was the surface area of a sphere if we'd heard it before, but this is how we get that. This is how we calculate it.